Okay, so here is the first of 4 videos that are going to talk through the modules for your Paper 1 physics exam. And the first one is to do with energy. The first thing I'm going to let you guys know is that energy is measured in a capital J for joules. Okay, so the first thing we need to know is about stores and transfers. So energy is a bit like money. Money gives you the ability to buy things. So with money you can buy things. Well, with energy you can do things, and energy can be stored in different ways, just like money. So money can be stored in a wallet, it can be stored in a bank account. Well, energy can be stored in different ways to allow us to do different things. So for example, energy can be stored in the kinetic energy store, which is the energy store for a moving object. Energy can be stored in an object that's off the ground, and we call that the gravitational potential energy store. So any object that is off the ground, we can say it has a store of gravitational potential energy. Any object that has been stretched or compressed, we say it has an elastic potential energy store. Any object that has had a temperature change, i.e. it's got hotter or colder, it's had a change in its thermal energy store. Any object that can do a chemical reaction that releases energy or absorbs energy has a store of chemical potential energy. And then the particles that are around us in the air in particular, they all have a amount of energy stored in them, and we call that the internal energy store, and all of which are measured in joules. Okay, now little notes on this, for example. Okay, kinetic energy should be fairly obvious. A moving object. Gravitational potential energy, an object off the ground. Elastic energy, a stretched or compressed object, that's important. Thermal energy, something getting hotter or colder. The chemical potential energy store, they're only going to really talk about three objects here. They can talk about a fuel, because you can combust a fuel to release energy. They can talk about a battery, because you get energy from batteries. Or they could talk about food, because obviously we combust our fuel, we undergo respiration to get our energy out of food. So food is an example of a chemical potential energy store. And then we go on to transfers. Now there's 4 ways in which we transfer energy. If a force is exerted on an object, for example causing it to move, we say the energy has been transferred mechanically. If you have transferred energy through wires, because you've involved a current, you've actually transferred the energy using some wires, we say the energy has been transferred electrically. If you transfer the energy via a wave, for example light and sound, we say that it has been transferred via a radiation pathway. And then finally, if energy has been transferred from a hot to a cold object, that's important, hot to cold, energy is not transferred from cold to hot, we say it's been transferred using the heating pathway. Okay, so you need to know that. Now here we're going to go through an example of how we can use stores and transfers, our knowledge of that, in an exam question. So here is an example of a scenario. We have a ball, and the ball is moving down the hill with a certain velocity. Now, if we just think about the scenario, the ball at the top of the hill, its kinetic energy at the start is 0, it's not moving. But because it's on top of a hill, compared to the ball at the bottom of the hill, it has a gravitational potential energy, because it is higher from the ground surface down here. We say at this point here it has its maximum gravitational potential energy. Now when we let go of the ball moves down the hill, and it gains kinetic energy and loses gravitational potential energy. Now really, energy is never created or destroyed, it's only ever transferred, and this is called the conservation of energy. So if we go back to our example, the amount of kinetic energy that's gone up is the amount of gravitational potential energy that's gone down. Energy is never created or destroyed, only transferred usefully, stored or dissipated. That is called the conservation of energy. So if we had an exam question that asked us to describe the changes in the energy stores and the transfers that occur, a perfect exam answer would be this. At the top of the hill, the ball has a store of gravitational potential energy. As the ball moves down the hill, the gravitational potential energy of the ball decreases as it gets closer to the ground, or the ground is lower down. The kinetic energy of the ball increases as it increases in speed down the hill. The ball moves down the hill due to the force of gravity. This therefore represents a mechanical energy transfer. Now I just need to break this down a little bit further. In your physics exam, if a question comes up where it says describe the changes in energy stores, it's very, very important that you do not just write how the energy store itself goes down. You must include the destination of the energy store. So let me explain. In this sentence here, as the ball moves down the hill, the gravitational potential energy of the ball decreases as it gets closer to the ground. I would not get the mark if I didn't have of the ball. If I wrote, as the ball moves down the hill, the gravitational potential energy decreases, I would not get any marks because I have not included the destination of this energy store. So by including of the ball, i.e. as the ball moves down the hill, the gravitational potential energy of the ball decreases, I get the mark. So whenever you talk about an energy store in your physics exam, you must include the destination, the object that you are talking about. Okay? So moving on to another topic, we have this idea of specific heat capacity. Now the definition of specific heat capacity that you have to write for 2 marks will be this. It is the amount of energy required to change the temperature of 1 kilogram of a substance by 1 degree Celsius without changing state. Now I'll tell you where the marks are. 1 mark is for actually writing 1 kilogram. That's very important. The rest of it is the second mark. Now it's governed by this equation, and the nice thing about this equation is it's one of the ones you're given. So if in your exam it says use the physics equation sheet, and it's to do with something heating up, and it's got this word specific heat capacity in it, you've got to go to this equation. So it states that the change in the thermal energy of an object is the mass times the specific heat capacity times by the change in temperature. Let's just break this down and think about what it actually means. Okay, let's consider this block. So here's a metal block, and this block is 1 kilogram. So our mass is 1 kilogram. And the block is being heated by this dubious looking flame, that is a flame, and it's being heated by Bunsen, let's say. Okay, and the specific heat capacity of this metal block is 500 joules per kilogram degrees Celsius. What does that mean? It means that it takes 500 joules to heat this 1 kilogram block up by 1 degree Celsius. So if we look at our table, here we have the amount of energy we put in. So let's say I put 500 joules of energy into this block. Well, because of its specific heat capacity being 500 joules per kilogram degree Celsius, it's going to go up by 1 degree Celsius. Let's say I put half in. So if I put 250 joules into this block, it's only going to go up by half a degree, because of the specific heat capacity being 500 joules per kilogram degree Celsius. Let's say I put 1,000 joules in. Well, if I put 1,000 joules in, because it takes 500 joules to go up by 1 degree Celsius, it's therefore going to go up by 2 degrees Celsius. And then finally, let's say I put 2,000 joules in. If I put 2,000 joules into this block, and it has a specific capacity of 500 joules per kilogram per degree Celsius, it's going to go up by 4 degrees. Now there's a required practical for this, and you are going to go through this required practical in the time before your exam. Okay, but just a quick mention about this required practical. It's a metal block. The metal block has 2 holes. It's got a hole for the thermometer, because you're going to record temperature, and it's got a hole for the heater, because you're going to heat the block up. And surrounding this metal block, or liquid, remember it could be a liquid, you have insulation. Okay, now here's the circuit diagram for this practical. You have your power source, you have a switch to turn it on and off, you have an ammeter to measure current, you have a voltmeter in parallel with the component you are measuring, so the voltmeter measures potential difference of the heater, and we have a heater. You don't need to know the circuit symbol of a heater. So what's going to happen in this practical is you turn this on, and the heater is going to heat the block up, and you're measuring the temperature. Using your equations, you can work out how much energy has actually gone into this block by the following method. You know power is current times potential difference. You know energy is power times time. So because throughout this practical you have measured current and you've measured potential difference, you can work out power. And then because during this practical you've measured the time it's taken for all this to happen, you do your power multiplied by your time to get how much energy has gone into the block. Now it's a rather kind of confusing and complicated way to work out specific heat capacity, but if this plot comes up, you will get a straight line, temperature on the y-axis, energy on the x-axis, and the gradient of that allows you to work out the specific heat capacity. The specific heat capacity is the change in energy divided by the mass times the change in temperature. So because of that, the specific heat capacity is 1 divided by the mass times the gradient of that line. Now you're going to go through that in more detail with your teacher before your exam, and if you didn't quite get the graph, do not worry, it would be a very, very high order question looking at separating grade 7 to grade 8 to grade 9. Okay, let's go on to power. Now power is the rate of change of energy. That is the best definition of it. It's the rate of change of energy measured in watts, and the equation you need to know is power is energy divided by time. So here's a scenario. I've got a motor, and the motor is lifting certain masses. Now this motor here takes 60 seconds to lift a mass of 5 kilograms, whereas this motor takes 60 seconds to lift a mass of 10 kilograms. Clearly, the one on the right is more powerful because in the same amount of time, it lifts a heavier weight. So it transfers the energy, more energy in the same amount of time. So it's more powerful. Okay, so that's kind of using power in a context. Then we move on to this idea of efficiency. Now, efficiency is simply a ratio of how much useful energy has been transferred divided by the total amount of energy you've transferred to it. So let's look at this light bulb. Here's a light bulb, and it's had 500 joules transferred into it. 200 joules has come off as light, and 300 joules has come off as heat. Clearly, the light is what we want from a light bulb, so that's the useful, and the wasted is 300 joules because that's the heat. So to find out the efficiency of this energy transfer, you would do 200 divided by 500, not 300, because it's the input, it's the total. So 200 divided by 500 times by 100, and it's a 40% efficient transfer. By all means, try and do that yourself. Stop the video and do it yourself. Moving on. Okay, so we have, you need to be confident in how we reduce certain energy transfers. There's certain energy transfers we don't want to happen. For example, a house. We want to keep a house nice and warm. We don't want this house to be nice and cool, especially in our climate. So we do certain things in order to reduce the energy that's coming out of our house. We put insulation in the walls. We put insulation in the loft. We put double glazed windows in, and we use little draft excluders to stop a draft going in and out of the house. Now, how much cooling happens in a certain amount of time? The rate of cooling of a building depends on the thickness of the walls and the thermal conductivity of the walls. So if you have a thicker wall, less energy is going to get out of the house because it's thicker. Thermal conductivity is just a measure of how easy it is for the energy to get through the wall. So if you have insulation, the thermal conductivity goes down because it's harder for the energy to get out because you've got insulation in there. Whereas without insulation, the thermal conductivity increases, relatively speaking, because of the fact that it's easier for the energy to get out of the house. Finally, energy resources. Okay, so there are renewables. There are renewables and there are non-renewables. So renewable energy resources, we have solar, the sun, wind, hydroelectric, wave, tidal, geothermal, and biofuel. Advantages of all of those is that no carbon dioxide, no greenhouse gases are emitted in using them. Non-renewables include not only coal, oil and gas, but nuclear as well. Okay, that is a non-renewable. Now, what do we mean by renewables? Renewable is the fact that these resources are replenished as they are being used. Okay, so you can replenish them as they are being used. Okay, now why do we generate electricity? What do we do it for? Well, we do it for three things. We generate electricity, we heat things, and for transport. Look how horrendous that car is. But anyways, for transport, okay, as fuel. Final things, final 2 minutes, guys. And what I'd recommend you do is stop the video at certain places here. You need to be really confident on equations. Your teacher's banged on about it for months and months now. You need to be really, really good at these, okay? You need to remember kinetic energy is a half times mass times velocity or speed squared, half mv squared. You need to know gravitational potential energy is mass times gravity times height. In the exam, gravity will be given to you as 9.8, so that's a clue. Use that equation. This equation will be given to you that elastic potential energy is a half times the spring constant times extension squared. This equation will also be given to you. The change in thermal energy is mass times superheat capacity times temperature change. Energy equals power times time, and efficiency is useful divided by total times 100. Now, a little tip that I've got for all of you is this. Look at the equation triangles. Energy is always at the top. So please ensure you're happy with energy always being at the top. Final minute I've got here is this. Okay. Here is a selection of equations, and I want you to stop the video and I want you to have a go at all of them. So stop the video now and have a go at them. Okay, and here are the answers using some Viva practice as well. Here are the answers. The first one is 160 joules. The second one is 70.56, so 71 to 2 significant figures. If the question wants you to do that, that will be 1 mark. Please remember that. See, the question gives you 9.8. The next one is elastic potential energy is 0.1 joules. Remember to convert extension into meters. Next one is power is 20 watts because you need to put kilojoules into joules. And finally, the last one is an efficiency of 68.75%, which to two significant figures, if the question wants you to do that, is 69%.